about 6 principles. 6 principles of sustainable design. I really like this framework. It gives you a good kind of sideboards for thinking about sustainable design. And in doing your second assignment, you get to apply them to a site and think about, how they might work. So what I'm going to do to give us maximum time for the watershed explanation and all that is I'm going to go through these fairly quickly. I have in the curriculum to review them tomorrow. What we're going to do when we review them first thing tomorrow morning is I want you to think of examples of how you would analyze a site for these 6 principles. Like how would you do it in your paper? Okay, because that's a hard part. All right, so respect. Let's see where we're at. All right, respect for the wisdom, and they all start with respect. I love that. You've got to respect these things, right? Wisdom of natural systems, biomimicry. So this one's kind of hard to get into design. What does nature do? It does all these things that we're talking about. It runs on sunlight. Well, our designs don't run strictly on sunlight. Even my house, I could get it pretty close, but you gotta run on sunlight. They only use the energy they need. Boy, what a system. No waste, no nothing. They fit form to function. The internet can be such a wormhole that you just fall down into, right? Somehow I got on a page about birds' nests and how they fit how they reproduce and how they fit form to function. Smaller birds that are worried about larger birds preying on their young can sometimes do pouch type of nests where the young are, where there's a hole at the top and then the babies are down in this pouch, so they're less accessible. It's just form function. My spouse and I get on this all the time. I'm 100% function. It's got to function. If I found a humidifier that did everything I wanted it to do, I wouldn't care what it looked like. My spouse is all form. Doesn't matter if it does the job, as long as it looks good. Nature doesn't care about that. They fit that form to the function that they need. They recycle everything. They reward cooperation. They bank on diversity. That's what nature does. An interesting point, a little story that could go with any of these. There was a native, like a water buffalo or something in Africa, and they wanted to repopulate it into other areas, regenerative design. They wanted to regenerate that habitat. One thing was missing. The dung beetle that was associated with that water buffalo didn't get moved with the water buffalo. So guess what happened? They had poop everywhere because that dung beetle wasn't eating the feces, so the natural system wasn't working the way it was supposed to. So they need that diversity. They demand local expertise and materials. I have local expertise in cleaning up water buffalo poop, so I must be part of this system. And we see that in nature all the time. Local experience and materials. Birds can't ship in mahogany from South America or wherever it comes from. They've got to use local materials. Wish we could do that more. I think you were talking about that, Adam, where you use rock that's on site and anything that you can find on site that you use. Perfect, because that keeps all the microbes. Even the leaves in the fall. Leave the leaves. I did a Leave the Leaves campaign at one point. They've done studies now on the microorganisms that live in leaf litter, and boy they want that to be there to help the soil, and there's all kinds of stuff that goes on. We don't even know. They curb excesses. One part of the population gets totally out of whack, it dies back. There's that curbing, and it taps the power of limits. They keep their own sizes of populations in check if we're not messing with them. Okay, so next principle, respect for people. it is really all about us. But it looks at this equality between humans and nature. Right now, we are totally dominant over nature. We need to come into a more egalitarian relationship. And certainly laws that are good for nature are good for people too. What's a law that's good for nature? Oh, I apologize, that's me. That's good for people too.
Well, it's not a law, it's a code, but in the district, I'm sure there is too. If you take down a tree at a certain caliber, you have to replace it with other trees, or you can't take it down.
Okay, well that law's not really good for nature. Nature would rather that the tree stay.
Well, but at least it's replaced with others.
Right. So what about, I had an elected official one time go, I don't want you cutting down trees that look like this, and you give me trees that look like this. He wanted us to plant huge trees. And I was like, dude, you can't move anything larger than 2 inches, and in my opinion, I don't think we should be planting anything larger than 1 inch, because they all catch up over time. Everybody wants these big trees, immediate effect. So, I'm not sure where I was going with that. Oh, laws that are good for nature. How about stream buffers? Stream buffers are good for nature. How are they good for people? Keeps people out of flood zones, okay. How about that water that flows through something that has a buffer?
Prevents erosion.
Prevents erosion, yes. Keeps the water cleaner. How about the temperature of that water? If there's a buffer, the water coming through that stream is going to have a more even temperature. The worst situation in the world is to have a stream going through the woods and then that stream totally daylighted to the sun for a segment. Everything dies in that segment because of the temperature of the water. So there's no microbial activity, nothing running up and down in the streams. Not good. See, I keep giving you examples. You're going to have to remember those for in the morning. 7 generations. Love this. Love that little piece of art. Looking, at those different generations. So who said injustice anywhere is a threat to justice everywhere? We are caught in an inescapable network of mutuality, tied to a single garment of destiny. Whatever affects one directly affects all indirectly. Who said that? Oh, people. What weekend is it?
Martin Luther King.
Thank you. He was talking about social issues, but it could be used in an environmental context as well. We are all tied together. Oops. I think I've got it on there. Yeah. The single garment of destiny. Truer words were never spoken. Don't forget the wombat. If we don't pay attention to this, we're what?
Doomed.
That's right. Thank you. Okay, so these things are all connected. So we need to look forward as well as backwards. I had an intern put this slide together. I love this. Turning off turns me on. So energy and natural resources, conservation and renewable resources. If you talk about sustainability, this is probably the principle that has the most attention paid to it. We use our resources like we got lots of planets, all energy is solar energy. Is it really sustainable to import 1/3 of our energy at that time? That's how much we were importing. 60% of which is petroleum. Well, it's not. Let's look at the 3 legs of sustainability. Is it sustainable from any of those? Let's talk about that more tomorrow. I want you to get into the fun stuff. Oh, and process. This is the development review process in Prince George's County. A yes/no diagram. Now you think this might look a little complicated? That is a mass oversimplification of the development process. But it's all still a process. And if we were doing it right, there would be feedback loops. Do you see any feedback loops in this? where we go, okay, we get everybody to the table before we even start designing. That would be a sustainable way to do it. You get the architect, the engineer, the site designer, everybody in the room before you even put pen to paper or plotter to ink, okay? We gotta change the process that gets to the result. Okay, now we're getting into the good stuff. Bioregions. An area of land or water that contains a geographically distinct assemblage of natural communities. Whew. What would be a bioregion that you can think of that we're in, maybe? Chesapeake Bay Watershed? Mid-Atlantic? You could call that a bioregion, Mid-Atlantic? Because that's all kind of the same eastern deciduous forest, you know, the same forest you have in Virginia, you have in Maryland, just at different elevations. Good stuff, right? Similar environmental conditions, interact ecologically in a way that makes sense for them long term. But because of globalization, we've lost these special spaces. So let's talk about how you can measure bioregions. I really like this graphic because, first of all, it was a student who was looking at their watershed within a larger watershed within the state of California. And oh, by the way, California is in the United States of America. It's my nesting dolls, right? It's these different scales as you go up and down. So flowing, and I love what they said, flowing from a focal point of my home space out to the entire planet, I love this, through a variety of air, water, soil, vegetation, fauna, and social connections. Remember, it's the wombat, it's everything's connected. So that's in that bioregion, everything's connected. The world could be a bioregion. So just the different scales that you're talking about. So bioregions can be defined in a lot of different ways. I'm just trying to, in this class, expose you to a lot of the things you're going to be looking at in other classes, such as physiographic provinces. I love that. Nothing like a 25-cent word, physiographic provinces. Basically, it just means that these areas have similar geology, similar soils, similar slope aspects, those kind of things. So it makes sense, right? So this is coastal plain. What do you think you get in the coastal plain? What's that like?
Salty air.
Maybe closer to that, but you know, what's the landscape look like? Is it steep? Is it generally?
Flat. Pretty flat.
Relatively flat. Floodplains that are very wide. Stream valleys that are very wide. And the next time you drive the Beltway, you're going to think about this. I once told this to elected officials, and oh my God, they totally got it. I couldn't believe it. Because we were talking about an eco park that was right on the border between Montgomery and Prince George's counties, and we were trying to get them to put some money toward it. You drive the Beltway from here, and you go, oh, from here, from where I used to work. You drive counterclockwise, coming around through Prince George's. You start going up to the BW Parkway. You're going up, up, up. And it goes down a little bit. Then it goes up to get to 95. You're going up in elevation. And then it goes up to where 95 cuts off, and then comes down to New Hampshire Avenue, and then goes back up again. Are you visualizing? I've driven this road so many times I can do it in my sleep. You're transitioning to the Piedmont. So up in the Piedmont, you have rockier soils. Down coastal plain, we've got sandy soils. We've also got some clay soils. This is one of the most important bioregions for doing design, or elements to doing design, is what bioregion are you, or what physiographic province are you in. In Montgomery County, the stream valleys are very narrow. They don't have wide, flat floodplains. Because of their rocky geology, they're more narrow. One developer said to me, well, why don't you measure stream buffers the same way that Montgomery County does? I said, well, apply. We're completely different soils. We're completely different layout. We can't do things the same because of those differences. Geologic formation, river basins. So this is sometimes hard to visualize, but here's the Potomac River. Can everybody see? So here's the Potomac River. And its watershed goes all the way over to West Virginia. All the way over and into the Potomac River, right? So all of this land up here is the Potomac River watershed. Wow, they better be doing some good land use practices up there. Oh wait, it's West Virginia. Or Western Maryland. See what I mean? So many things are connected. The airshed is quite important. Why is the airshed so important? Which means how the air flows through a region. And these are all connected. What kind of rain did we get? Really bad for decades upon decades. Acid rain that was produced by burning fossil fuels and spewing all that stuff into the air. And then it would rain, but it wouldn't rain on the states that were burning it. It rains on everybody to the east, because the flow is west to east. Okay. Geologic formations, as I said, that can really make a difference in how the groundwater flows. So we want to look at areas that are similar. This is that hardiness zone map. For those of you who aren't plant people, this tells you so these are numbered actually 2 through 10. So if I had, I'm in the Northern Virginia region, I'm a 7, okay? So I look up plants, will that grow? Oh, it says hardiness zone 7, that plant will grow here. Well, where I live now is up in 5. So the same plants don't grow in these same places. We know that, right? But look at this. This is between 1990 and only 2006. There's been some updates to this too. The dark red are 2 degrees change. Or zone changes, 2 zones. Changing of 2 zones, that's huge over such a short period of time. And this is based on the coldest temperatures recorded and all that. So it's all science, it's not made up stuff. So changes are happening. So should we be planting only zone 7 plants here that are going to live 100 years like the sycamore? Or should we be planting plants that can handle a wider spectrum of temperatures? Hard to say. Okay, sewer shed, or noise corridors. Who knows why this is noisy right here in Prince George's County? Very, very loud. These are noise contours. 85 decibels is the highest one recorded.
Where was that?
In Prince George's County. Does anybody know why that's so loud right there?
Is that the stadium?
No. Yes, it was the she said, is it the stadium? Andrews Air Force Base.
Oh.
Huge cargo planes come in and out of there. It's very loud. And it's hard because there's some existing communities there and we've had to negotiate those issues. Okay, sewer sheds. You know that plumber only needs to know 3 things, right? What does a plumber need to know? Hot's on the left, cold's on the right, and it all flows downhill. Sewer systems are gravity fed. So in order to understand the design issues associated with sewer systems, you have to know that they're gravity fed. So when I'm designing these new houses up here and I've got to tie into a sewer line down here, I've got to make sure these are uphill from where that tie-in is. That can throw a whole design out the window right there. Okay, so now let's get into the fun stuff. I want to talk about watersheds because these are a great way to define a bioregion, okay? And I love this graphic because it shows the arrows and it's showing the water moving and all of that. I love it. So watershed is the groundwater, the surface water, everything that drains to a common point. okay? And here's a better graphic for it. So all the water, I'm a raindrop and I fall right here, I eventually flow to this point right here. If I'm a raindrop and I fall outside of this, I drain somewhere else. I'll end up in that river, maybe somewhere else, okay? So it's where all the water drains to a specific point. Now why is this important for you to know this?
I mean, that's how you can deal with stormwater management. You need to know how much water is in your watersheds and how much you need to make up for if you provide sewage overflow.
Okay, so if you're doing a stormwater design, you've got to know how much is coming in, how much is coming from. I'd really like to encourage you as you're going through this program to go out on sites and just stand in one location and see if you can discern all of the land area that's draining to that one point. I used to do landscape design and construction before I got into local government, and almost every project we did had a drainage problem that we had to deal with. So we got to know how much water is coming in. Adam, you wanted to add something?
Whatever's happening upstream is going to affect, whether there's farming with chemicals, runoffs, going to affect communities downstream.
And if it's developed higher up in the watershed, that water coming down is going to be faster, hotter, more of it than if that area is forested. So you've got to know your watershed, what's coming to that point on the site for you. So watershed, John was like, oh, we don't care about that, because we're going to talk about watersheds and reading topo maps. So this exercise has been a little bit challenging for the students in the past, so I'm going to spend a little more time on it with you all than I have with students in the past. There's 3 sets. Okay, pass those, please. We got some extras. So, who here would consider themselves fairly comfortable with reading a topography map? Oh, a little bit. Okay, anybody over here feeling comfortable reading a topo map? You want to learn about it? Okay, let's do it. That just helps me in setting up the groups so that all the lost people are not together and trying to figure this out. So what I wanted to do here is purposefully, aren't I slick, put these slides on this one so we can do this. So follow along in the handout. I've got the same illustrations as you have in your handout. So you've got point A here and point B. So let's say they walk, one person walks along point A, one walks along point B. These are points of the same elevation. Okay? So if I was to draw this hill, it would look something like that. So each of these lines is a point of elevation. Does that make sense? So if I was hiking and I went up here, I'd be like, oh, that's a really easy hike, right? The contours are far apart. That means less of a slope. But what if I was hiking up this way? That's going to be steeper, right? Because the contours are closer together. And that, if I do this way, when you look at this from above, these lines are going to end up very close together on that side of that hill, okay? The hard part about this is taking 2 dimensions and making it look 3-dimensional in your mind, okay? This is so important to your work as you're working through the program that I really want you to get this part. So, stop me if you have any questions as we're going along. So then on the next figure, it says, well, this is a little more logical. I lost the top of it, but that's okay. So here's the similar, one mound. You have two mounds together. Then this is called a saddle. And it makes sense, right? I'm like, hey, I could swing my leg over and I'd have this big hump behind me and I'd have the other big hump in front of me. Kind of looks like a saddle, right? But what's really important on this one is showing which way the water flows on the surface. So if you're at the top of this mountain, you're going, oh, okay, this is going this way, this is going this way. And you always draw these perpendicular to the line, because in theory, water's going to run straight down the slope. Okay? So at a saddle, the water's going to go this way and this way, because this is flat right here. I looked up my house on the, you can go on usgs.gov, I think, and pull up any of their topo maps across the country. So when I was looking at my house, I was like, well, let me look at the topo and see what's going on. I was like, yay, we're in a saddle, which means we're a little bit protected. But you know what that means? We get wind whipping through there like crazy, coming through those two high points. So I want you to get a feel for, this is a little more complicated type of design, of situation, okay? So you're always drawing those arrows perpendicular to the topo lines to figure out where the water's going. Okay. So the next step then, the way this model talks about it, let's talk about what happens when there's a stream. I want a blue marker so bad. Okay, so here's the stream. A stream is usually depicted with 3 dots and a dash. So you got a stream that goes that way. This one's only got 2 dots, and that way. So you see that these are streams coming through here. Topo lines always point upstream. So let's think about that. This is a little hard to illustrate. But say you've got a little canyon like this that has a stream down in it. And if I was to, how can I do this? If that makes sense. Oh yeah. Okay, so these are points of equal elevation, right? So if I'm doing this in 3 dimensions, if I was to look down on these red lines, they would point upstream. Okay? So you can tell from looking at this that the flow is to the bottom of the page. The flow goes that way, because these are pointing upstream. So this is a common point of elevation. You can almost visualize the canyons that these streams are creating. So to delineate the watershed, this is E3. Let me come back to that. Oh, this is just showing an idealized watershed, very simple design. It goes from these high points through that saddle, and it all drains to this common point right here. I'll go into that in a little more detail in the next 2 examples. Okay, everybody with me? It's late afternoon, you still with me? Okay, we're doing it. Because I'm going to give you maps and you're going to do this yourself, okay? Because this is really important that you can read this and understand it. Okay, so here's a wetland that's in a stream. So here's the stream. It's creating these wetlands, blah, blah, blah. We need to know how much land area is draining to that wetland, okay? So the first thing that they do in this method is they go around and they X all the high points. makes sense. And they've done it all the way around that I can't reach. And then if they say, okay, this is the point that we're measuring from for these wetlands. So then they connect these high points. And it's a lot more complicated than what I'm doing right now, but I'll show you how to do that method as we're working through that. So last slide for this is the actual delineation. So the step that they left out that I would do is which way is the water flowing on every one of these contours. So I would go like this. This is going this way, this is going this way. So this is in the watershed, this is out of the watershed. Right here, perpendicular is that way, perpendicular is that way. Ah, okay. So the line needs to go through here. See how it's, if you ever get stuck, just start writing those arrows perpendicular to the contour lines, and that'll help you visualize. Or if you get stuck, just go, I'm a drop of water, and I fall right here. Where am I going based on the topo lines? Am I going towards the stream or away from it? Okay? So then that's what they did to get this. They said, you know, right here, here's my perpendicular. These are going this way. Perpendicular, these are going this way. That's going this way. That's going this way. So only this part that's draining towards that stream is included in that watershed. Okay? So I'm going to give you, so for the last 40 minutes or so, we're going to take these topo maps that we put together that I've got printed for you. Who is the comfortable-ish ones? So you're comfortable-ish. Why don't you keep your same 3 that you did your last exercise with? Was there somebody comfortable, or are you comfortable-ish? Do you want to? Okay. So keep your same group then, and you 3 be okay together? All right. So let's do that. I'll give you these. We'll turn the lights up.
I just did a sticky processes, and then there was like.
Oh, you know what? I needed Karen's.
Thank you. I have no idea how it is.
Yeah, you can